Hi everyone, welcome back to another series of the NL seminar. Today we have Zixiang Chen, Ph.D. student from UCLA, advised by Professor Quanquan Gu. He got his bachelor's degree in mathematics from Tsinghua University, and his general interest is in deep learning with a focus on generative models, representation learning, and multi-agent reinforcement learning. Recently, he's been actually using AI to enhance scientific discovery in the domain of public health. And he's been a visiting graduate student in the Theory of Reinforcement Learning program at the Simons Institute for the Theory of Computing. So without further ado, let's please welcome Zixiang.
Thank you, Justin, for the introduction, and it's my great pleasure to share our recent work at the NL seminar today. I will be talking about the self-play fine-tuning converts a weak language model to strong language models. It's a joint work with Yihe, Huizhuo, Kaishen, and Chen. So nowadays, the deep learning model becomes larger and larger, and especially for large language models, it has many parameters, and it is pre-trained over the data set that collected from the website, and it has the ability to dealing with many different tasks. To align the LLM's output with the human needs, we need to fine-tune the pre-trained LLMs for specific tasks. There are two popular methods. One is the supervised fine-tuning method, SFT. Another one is the reinforcement learning method, IO fine-tuning. So for the supervised fine-tuning method, we need a high-quality data set that's collected from the human responses. And we use the core entropy loss to fine-tune it. And the reinforcement learning fine-tuning is typically after the SFT for better alignment. And for that one, we generally need the preference data set that annotated by the human or the AI. No matter which method, the collection of the high quality data is always expensive, and those data sets are quite variable. Therefore, there is need for the researchers to explore the method that can make the full use of the SFT data set. So our method is actually doing the way that for the supervised fine-tuning. So the first question is that whether the core entropy loss is already powerful enough to unleash the full power of the high quality SFT data. So we observe that there can still have a persistent quality gap between the ground truth response from the supervised fine-tuning LLM and the target data distribution from the SFT data set. So this is an example. So the prompt is that in Southampton, what is the most popular form of the transportation for commuters? If we look at the response from the SFT data set, it tells us that it doesn't have the access to current data, but historically, the most popular form of the transportation for commuters is the buses. And the LLM, which is supervised fine-tuned over the data set, it gives answer that 55% of the commuters in the Southampton use a car as a primary mode of transportation. So this is a very accurate answer, but this is a hallucination. The reason is that the LLM in these cases, it doesn't have the access to the updated data. And also the 55% commuters use the car as the primary method to transportation is also not correct. So the question is that whether the LLM itself can notice the difference between its answer and the answer from the SFT data set and further get self-improve. So the answer is yes. So we introduced a self-play fine-tuning method. As you can see from the right-hand side figure, our method is actually an iterative method for the self-play fine-tuning. And after each iteration, the performance of the LLM will get increased from the 58 to the 63. And our method has two distinct features from the SFT method using the core entropy loss. The first is that we require the LLM to generate its own training data for its upcoming iterations. Therefore, the LM will use the synthetic data as the training data. The LM refines itself to distinguish these self-generated responses from those obtained from the human annotated data. So these two features together gives our method a better performance compared a better conformance after the spin. We call our method as a spin, and after the spin, we can improve the LM's performance. Okay, so this is a continued result for the previous example. As you can see from this block, after the first iteration, the model will actually give a better response. It will tell you that the LM doesn't have the access to the latest updates, but based on the previous report, the most popular transportation method is actually the public transport network, which includes the buses. Okay. So before wait a minute, I forgot to mention one thing. So if you have any questions, feel free to raise your hand and ask. I'm more than happy for that. Okay, so before I introduce the detailed mechanism of the spin, I would like to introduce the problem setting first. So we denote the input sequence as X, which consists of different tokens x1 to xn, and we denote the response sequence as Y, and we use the p theta given X to denote the LOM. And here the theta lies in the parameter space big theta. We're considering the autoregressing model. Therefore, the probability p theta y given X can be decomposed using the Bayesian rule from the position from left to right. And we call this set, the p theta, for the theta belongs to big theta, this as the LM space. This is what we want to optimize. Okay, now I'd like to introduce the self-play mechanism. So this is a two-player game. We have one main player and another is the opponent player. The main player wants to distinguish the opponent's responses from the ground truth responses. And the opponent player wants to generate the responses to be indistinguishable for the main player. And although there are two players, but the two players are acted by the same LLM. Therefore, we will only maintain one LLM during the optimization. The main player will be acted by the LLM as the current iteration, which we want to optimize. And the opponent player will be acted by the LLM from the previous iteration, which we want to update. Therefore, the spin consists of the following two steps at each iteration. The first step is training the main player, and the second step is to update the opponent player. Okay, next I will introduce the training and the updating one by one. Yeah. Okay. A main player is denoted as the function f. It will give you the value. When given the input x and the output y, the function f will give a value. When the f is large, then the main player thinks it comes from the p data, which is the target distribution. And if the function f is small, then the main player thinks it comes from the LLM's generated data. And therefore, the main player is going to, and we want to train the main player through this equation. This equation wants to maximize the gap between the adaptation of the value of f between the p data and the p theta t. In practice, we added a loss L here. the L should be monotonically decreasing and convex. By introduce the L, we convert the argmax problem to the argmin problem because it's monotonic decreasing. And the meaning of the function f remains the same. The higher value of the function f means that it comes from the p data, and the lower value of the function f means that it comes from the LLM. And you may also notice that here we have the function class ft. So this ft is a function class at the iteration t plus 1, which needs to be chosen later. This function class is very important because it determines what your mean pairs comes from. And also, we would advise that this function class should be compact enough so that it can capture the difference between the p data and the p theta t. Okay, but now we will just leave it as a placeholder. Okay, suppose we have already changed the mean pair at the iteration t plus 1. So how can we update the opponent pair? Recall that the opponent pair want to generate the responses that is indistinguishable for the mean pair, right? And the mean pair uses the function value f to determine whether the example comes from the p data or comes from the LLM. Therefore, the opponent pair aims to generate a better data by maximizing this function. As we can see here, this term is actually going to maximize the function f to make it indistinguishable from the p data. And we also added the regularizer here. This regularizer is a KL divergence from the p to the p theta t. The p theta t is actually the opponent pair from the previous iteration. So the reason that we want to add this regularizer because we don't want we want to stabilize the training. We don't want the opponent pair at current iteration get too far away from the previous iteration, which will make our training unstable. So the lambda is a hyperparameter that controls the strength of the regularizer. When lambda equals to 0, there is no regularizer at all. When lambda goes to infinity, then it means that the opponent pair will just to be simply copy the previous iteration. Yeah, what's the question?
So here's a question from the chat. Can the speaker discuss the difference between this and GAN? It sounds like a GAN at a high level.
Yeah, actually we share the same concept with the GAN, because in the GAN, it also uses the discriminator to distinguish the data distribution and also the generated data distribution. Here, the key difference is that we'll show later that our function class, we will only evolve one LLM, which means that the mean pair and opponent pair, not two different networks, but they are the same LLM, which is one is the previous LLM and one is the current LLM. So from this level, you would consider me that this two-player game more like the game of the Go, because in the AlphaGo 0, it's also the previous iteration of myself that compete with the current iteration of myself. Yeah. Cool. So I will continue here. To solve this optimization problem, the naive way is to put this probability P into the LLM space P theta and optimize it with the gradient descent. But surprisingly, this term actually had a closed form solution, which equal to this one. The P hat is proportional to P theta T times 2 multiplying the additional term, which is determined by the mean pair ft plus 1. So let's considering. So it would be very nice if we can use this closed form solution P hat directly as the update of the opponent pair. because if we can do that, we can save the computation budget, and also we can make the whole process more stable because we don't need to do the 2-time scale optimization, right? So can we do that? The key point is that we need to make sure that this closed form solution P hat belongs to the LOM set. But this may not be true. The reason is that the P theta T must belong to the LOM set, but we need to multiply in an additional term, which is determined by the mean pair ft plus 1. So a natural question is that, can we select a good function class so that the P hat belongs to the LOM set itself? Okay, so in this slide, we will show that how to choose the function class. Recall that previously we set the function class as a placeholder, right? So now we are going to choose the function class. If we want P hat belongs to the function class, we know that there must exist a theta so that P theta equal to P hat, which gives this formula P theta proportional to P theta T times multiplying this factor. So we can solve this equation, and we give ft plus 1 equal to lambda times log P theta divided by P theta T. Here we ignore the constant terms. So this suggests us to using the following function class. The ft equal to lambda times log P theta divided by P theta T. And theta belongs to the parameter space big theta. Okay. Now we have chosen the function class. So what will happen? From the previous slide, we know that the mean pair ft plus 1 will be learned through by minimize that objective function. And now, since the ft plus 1 lies in this function class, which is parameterized by theta, there must exist a theta t plus 1 such that the ft plus 1 equals to lambda times log P theta T plus 1 divided by P theta T, right? And then we can plug in the mean pair, this term, into the closed form solution, this one. And after simple algebra, we get that P hat equals to P theta T plus 1 y bigger x. Okay, therefore, we know that the mean pair and opponent pair are all parameterized, can all be represented by the LOM space. And for the mean pair, it is actually represented by the P theta log P theta T plus 1 divided by P theta T. And for the opponent pair, it's just P theta T plus 1. Okay. So as you can see here, the mean pair and the opponent pair share the same parameterization, and the cell plane only involves the old and new version of the LOM. And this is the key difference between our method and the gain in the image generation. Okay, as you can see from this whole cell plane mechanism, the opponent as a pair as T is the P theta T. And we train to get the mean pair at T plus 1, which is lambda times log P theta T plus 1 divided by P theta T, to distinguish the example from the opponent pair and the target distribution. And then, given the mean pair, we can update the opponent pair at T plus 1 using the co-form solution. We get the P theta T plus 1. And this is what we did as the iteration T plus 1, and the whole process will continue. Okay. So in this slide, we'll give the end-to-end training objective function for the theta T, because we know that both the mean pair and the opponent pair will be parameterized by the theta, right? So once we learn the theta T plus 1, then the whole self-play training procedure will actually be determined. Recall that in step 1, we get ft plus 1 is changed by minimizing this objective function. And in step 2, we choose the function class as this one. So we can integrate the two steps together to get a single end-to-end training objective function for the theta t plus 1, which is mean, which is get by minimizing the L spin loss. Looks like this one. So the red equation is directly derived by plugging the function class ft into the first step. Okay. Cool. So now we come to the final algorithm. As you can see here. So what we do for the self-play fine-tuning the spin, what we require is the FFT data set, the xi, yi, and the LLM with the parameter theta 0. This LLM can be already SFT at this data set using the core entropy loss. And the big T is the number of the iterations. For each iteration, we will first generate the synthetic data y prime, and then we will calculate the empirical L spin loss, and then minimize it to get the theta t plus 1. Therefore, we will get the theta t plus 1, theta t plus 2, and until we get the big theta t. And what's the LOM? We finally get is the p theta t. Okay, and this is the our full algorithm, and the mechanism behind our full algorithm is the self-link. Okay, cool.
So we have another question from the online audience. Zixiang Chen asked, what is the key difference between spin and iterative DPL and self-generated preference pairs?
Yeah, so in our cases, we will generate the synthetic data y prime, right? And as you can see here, the generated y prime is what our model generated as the current iteration. So this is one difference. Another difference is that our method is based on the self-play, and we didn't, and we want to match the target distribution, right? So in the intuition, they are different, and also technically, if you look into our algorithm, you will find that given the xi, the yi prime, and yi, they are actually independent. But if you're considering the DPO or iterative DPO for their cases, the winner and the loser, they should they are not independent given xi, because one is the winner, one is the loser. They are differentiated by annotated by the human, right? So which means that one is better than another, and if you write down the mathematical formula, you will find that the winner and loser themselves are not independent. So both in the technical cases and also the head of iteration, we actually is different. Yeah. But we admit that for the algorithm and also for the loss function, they look the similar. Cool. Yeah, I think I can stop here for 1 minute, for another 1 minute, so to take the questions if there are any.
So you're seeing one of the main benefits is having a single model do both the opponent and the main player,
right?
Again, where it had a separate discriminator and a generator.
Right.
What is the main benefit of having? Is there a theoretical benefit for having a single model do both compared to having separate?
Well, I think if for theoretical way, if you train the both network to be the optimal, I think they will come to the same end. I mean, you will match, they will align your LM with the target distribution. But again, we all know that the GAN suffers from the model degenerate issues, and also if you want to maintain two networks, you need to pay twice a computation budget. And also the training can be unstable, and you need to tune the parameters carefully. Yeah.
So from a technical standpoint, managing two models is more difficult than managing one, and you show that it's easier to train just a single model.
Right. And also also in methodology, right? It's a self-play method, and we believe that through the self-play, the model itself can actually become stronger and stronger, because such a phenomenon has been observed or actually applied for many areas, especially is for the alphago zero, right?
Okay. Another question. So even though it's the same architecture, but actually the two models are different, right?
Right. As you can see here, the mean pair will actually act as a lambda times log p theta t plus 1 divided by p theta t, and another one is the p theta t. So the mean pair and the opponent pair, they are all represented by the same LLM, but in detail, the formula would have the difference. Yeah.
Mm-hmm. So I guess so here is the similarity to GAN, that you actually have two different parts that are, one of them is doing the discrimination, the other is doing generation. And I guess the one of the nice advantages that you have here is that the LLM is both capable of generating and also discriminating, like basically classifying for you. So instead of classical GAN, which was like the discriminator was decoder part, and like the generator was a decoder or something like that. Here, the same architecture is capable of doing both the tasks. So yes, you can have two copies of it and use the same architecture for fulfilling both the tasks.
Yeah, that's true. So what's surprising is that for the LM, it can play as a generator, but it can also play as a discriminator. So this is very interesting things. And also, why the LM can do that? Because we can get the p theta through the LM. But if we're considering the original GAN, it will not give you the probability, right? Cool. Okay, now let's continue. I will first discuss the theoretical guarantee of our method, and next I will discuss the experiment result. Okay, so previously we have mentioned that we introduced the loss function L, which should be monotonically decreasing and also convex. So this is a very weak assumption, and it can be satisfied by many laws, including the correlation loss, the hinge loss, and also the logicity loss. All of these three are actually very popular in the machine learning area. Okay, based on the assumption one, we can have the following two results. The first is the sufficient result if the current LM p theta t is already aligned with the target distribution p data. Then we can conclude that the theta t is the global minimum of the L spin, which means that the theta t plus 1 must equal to the theta t. And therefore, in the next iteration, the theta t plus 2 must equal to the theta t plus 1. So the whole algorithm will naturally stop. And the second result is the necessarity result. If the current LM responses to the p theta t not equal to the p data, then there exists an appropriately chosen lambda so that the theta t is not the global minimum of the L spin. Therefore, the theta t plus 1 not equal to the theta t. So these two sufficient and necessarity results together give that our algorithm naturally stops when the LM aligns with the target distribution. Okay, so this theorem works. Okay.
Isn't the sufficiency compounded? If you fulfill that equation, doesn't that mean you're like basically memorizing the data distribution?
Oh, what?
Aren't you like memorizing the target data distribution like completely rather than some kind of generalization?
Well, actually here we make the distribution level, right? If you're considering during the code entropy loss, the global mean method, you also actually achieved when the p-sat equal to the p-data. So, so you see the distribution level to say that our algorithm, the self-play mechanism, will naturally stops when the p-data, p-sat equal to the p-data. Yeah. Okay, cool. This theorem is for the general cases because it works for all the loss functions that satisfy the assumption one. If we considering the choice of the logistic loss in the spin, then we will have a more detailed analysis. And the logistic loss is also the loss that we use in our experiment because we find it is the most stable loss. Okay. We have the following result. The p-sat t plus 1 will actually proportional to the p-sat t multiplying this factor. So how to explain this result? So as we can see from this factor, when p-data is larger than the p-sat t, then we can see that the p-sat t plus 1 will actually goes up compared to the p-sat t. And if p-data is smaller than the p-sat t, then the p-sat t plus 1 will actually go down. So these two results together show that the p-sat t plus 1 will get closer and closer to the p-data. And this also aligns with the previous, the theorem in the previous slides. We show that our algorithm naturally stops when the p-theta equal to aligns with the p-data. Okay. And also, this factor is regulated by the factor lambda. When lambda goes to 0, as we can see, the p-sat t plus 1 actually will change greatly. But if lambda goes to infinity, then the p-sat t plus 1 will just simply equal to the p-sat t. So this observation also aligns with the iteration that we introduced the k regularization for the opponent pairs updating. Okay. Cool. So next I will talk about the experiment result. So we consider fine-tuning the alpha 7b as ft full. This is the checkpoint from the Hugging face that is fully SFT over the dataset ultra-track 200K, and the base is the mixture 7b. The dataset ultra-track 200K is a high-quality subset of a larger ultra-track dataset. And in our experiment, we only require the ultra-track 200K. We didn't include the additional human annotated data. And in detail, for each iteration, we will randomly sample 50K prompts from the ultra-track 200K and generate the model responses accordingly. And we use the Hugging face open LLM leaderboard for the evaluation. And it includes 6 different data sets. Each of them will focus on the specific capability of the LLM. For example, the reasoning, the mathematics. Okay. And this is the bar chart of our experiment result. Let's first look at the average, one. So if you look at the first bar, this is actually the alpha SFT. And the second bar, this is the alpha DPO, which is further fine-tuned using the RL method on the additional human annotated data set. And the last 4 bar is actually the results for the spin from the iteration 0, 1, 2, 3. So as we can see from this bar, starting from the first iteration, our method can bypass the verify SFT, and starting from the second iteration, our method can even outperform the model that uses additional human annotated data. And through each iteration, our performance will actually get better and better. And you can also look at the detailed performance over different data sets. As you can see over the figure, our method can actually universally improve the model's performance. Okay. So in the previous slide, we have shown that spin with the synthetic data generation can effectively improve the LLM's performance. But we can show that in this slide, simply SFT again using the co-entropy loss will only degrade the performance, as you can see here. If we continue SFT for the first checkpoint delta 7b SFT full, then actually the result will actually go down. And we also did a more detailed analysis. The blue one is the SFT the checkpoint that use the SFT method, and we train by ourselves starting from the initial Mistral 7B model. So as you can see here, when the training size goes up, the performance will only fluctuate and they will not go up. But if we use the spin, even with only 50K training size, the result will actually goes up, and this is only one iteration. Okay, so we have shown that using the spin with the synthetic data generation will greatly improve the model performance, but will the iterative training really necessary? So in this slide, we'll actually analyze whether what happens if we only train for one iteration, but for very, very long epochs. So as you can see here, if we train for the iteration 0 for a long time, then the performance of the model will actually reach a limit, as you can see from these three figures. Further extent, the training process will not give a better result, but this limit can be breakthrough during the next iteration. The dashed line is actually the performance of the LLM after spin for the iteration 1 epoch 2. So as you can see from this three figure, we can tell that the iterative training really helps.
Question?
Yeah.
So when you're saying that you're training for one iteration but for multiple hops,
right?
Do you still have like in the original method you had a single sample from the model for each data point, right?
Right.
Do you now have the number of samples from the original model equal to the number of epochs, or are you already using the same sample?
Oh, we are using the same example by the training for a long time. Yeah.
So you don't draw the
yeah, actually we don't draw the friend examples. Yeah. But for the iteration 1, we also use the same prompts. Yeah, we always use the same prompts.
Well, the prompts are the same, but you have the Y data and
Y I see. You mean whether the Y data will be flashed?
Y data is always the same. It's your data, but
Y prime.
Yeah, Y prime is what
yeah, for this experiment, actually, the Y prime won't be flashed. Yeah, they will keep the same, but only the training for a long time. Yeah. Yeah, that's a good question. Cool. And we also did the additional model evaluation on the MT bench. So this is an evaluation for the writing, role-play, reasoning, math, coding, and extra. And as you can see from this radar figure, after spin, the model will actually get improved over the writing, the role play, the reasoning, and the coding. The reason that it didn't get improved over the math may cause that the 200K ultra chat, they didn't include they didn't include the math related examples. Yeah. Okay. So, in summary, the spin converts the weak LM to a strong LM by unleashing the full power of the human annotated data. And we introduced, and the key technique is a self-play mechanism. And the mean pair aims to distinguish the LM's response from the target distribution, and the opponent pair aims to generate the undistinguishable examples for the mean pair. And through that method, we empirically show that the LM can train through spin to outperform the model trained with additional human data or AI feedback. And the interesting direction in that, or the promising direction is to exploring the dynamically changing SFT data set. Because in our environment, we set the SFT data set or the target distribution to be the same. I mean, it will not change. But if we want our LM to get self-improved to even superhuman, then we would like to considering that whether this SFT data set can dynamically change based on your model. I mean, when your model gets stronger, your target distribution also gets stronger. Yeah, this will be very interesting future direction. And I think there are also several minutes left, so I would like to use 3 to 4 more slides to show how the self-play fine-tuning can even help for the diffusion models. Okay, we know that for the LLM, it can not only generate the text, right? Nowadays, GPT-4 can also generate the images. So, and for that generation, we use the diffusion. So for the text to image generation tasks, we also want to align it with the human needs. We can use the supervised fine-tuning or the IO fine-tuning. So as you can see on the right-hand side, what we really cares about is that whether the contextual, whether the context and the image, they get aligned with each other, which we call the contextual accuracy. And also we care about the aesthetics or the visual appeal or the high resolution images. Okay, this is a JD card holding a lightsaber. So as I have mentioned before for the GAN, what's really challenging for the image generation is that we don't have the probability, right? We don't know what the probability is. So how can we use the spin? So for diffusion models, we know that based on the previous steps, the current step is actually a Gaussian, right? Then we can use a sequence of Gaussian to calculate the probability, the log probability of the generated data. And in detail, the mean pair will use access to the marginal probability P theta x0 continue on the context C, and requires the integration from, it will actually distinguish not only the last generated image from the target image, but it will try to distinguish 2 diffusion processes. The first diffusion process is the generated diffusion process, and the second diffusion process is the target diffusion, the forward process. So the main pair is to distinguish between the process rather than just the examples. And the opponent pair will actually update it according to the main pair to make the diffusion process to be the better. And the training objective looks like this one. And this is our newly released paper about three weeks ago. And the model's trend point is also uploaded to the Hugging Face. And this is the image. As you can see that through the self-based and tuning method, it can, if we didn't use any zero fine-tuning methods, then if we put into the test a snowy Chicago street during the Christmas art, there is no Christmas phenomenon at all. If we use the FFT, we can see the Christmas tree. If we use self-play fine-tuning, actually the phenomenon will actually get aligned with our humans' feelings, and you can see that the Christmas tree becomes more visually appealing. Yeah. And this is a collected gallery. So I think I have finished today's talk, and I would be, I'm very grateful that you can come to listen to the talk, and our results have been, our project website have been released through this website, and you can find our code on GitHub, and also our data and models have been uploaded to the Hugging Face. If you are interested in the detail, you can scan this QR code, and you can find our archive paper. And thank you for listening, and I'm ready to take the questions. And if you have more detailed questions, and also feel free to discuss with me afterwards. Yeah, thank you.
Yes.
Yeah.
Do you go back to the OpenLLM benchmark?
Yeah, sure.
Yeah. Why do you think it underperforms on MMLU and
Yeah, that's a good question. I think the question would still the same with that empty bench for math. It would be the cases that you know that when you fine tuning the LM, when one goes higher, another may get lower. It's called the forgetting, right? And also for this case, because we only use the UltraChat 200K, and many aspects may not be included. So I think the MMLU may be increased if we considering a variant of the data set.
Could you go next?
Okay.
Just two more slides.
Okay.
To the graph that shows.
Yeah. This one? Okay.
Yeah, so these are all from the MMLU set, right? So MMLU has humanities, STEM, writing, these all of these. So here we see that it kind of performs similarly or better always, but we don't really see that in the MMLU result in the open.
Oh, you mean which one? You mean which performance?
So here we see that on all of these tasks, it performs almost equal or better always, but all of these tasks are also in the MMLU set. But we do see that MMLU has...
I think it was...
What you showed.
I see. I think it would be due to that for the empty bench we use the evaluation record we use are different. Yeah.
Question. So when we say human annotated data, do you mean the data is about classifying something? What kind of annotations do you have?
Oh, I see. Okay. So in our talk, for the human, it's just the task specific data set. For example, the LChat is actually you chat with the GPT-4, right? And also the human annotated data can come from the user and the high quality data set that human AIs chat, and also it can be those data sets that's selected from a bunch of the data set which had high quality. So this is the human annotated data set. And also for the for example, for the IO fine tuning, you will use the prevalent data set, right? This is also the human annotated data set. So why? Because we will have two responses. and the human will annotate which one is the winner, which one is the loser. So this is also the human annotated. Yeah.
Cool. Yeah. So 2 slides ago, you have the comparison with supervised fine-tuning, and here. So, could you explain why the 0 point is?
Okay. Yeah, it's a good question. So actually, here for this one, the 58 0.14 this point is actually the same as this one. So if we starting at this point and use the SFT, then actually it will go down to the 57, right? And this one is actually we train by ourselves using the SFT from the initial mixture 7B, and it will give you a better result for the SFT dataset. If we directly use this, the same trap point, it will only go down. Yeah. I mean, this one is actually what we used. We just used the trap point that's through that's released on the Hugging Face. We use this trap point. It goes out, and
so the horizontal axis is training size. If you are looking at point 0, then what data you are training on the training size is 0?
Okay, so actually this blue one, if you use the same trap point at the 58 of the 14, actually this result we can see that it's 57.23. So it will actually go down to beyond this figure, and this blue one is actually their trap point actually is different, because this one actually what we trained for one epoch in our own GPU. It's not the Hugging. It's not the trap point that's from the Hugging Face.
So then why didn't you?
When you train on which data your training size is 0?
Oh, what?
Like what is the horizontal axis mean? It says training size, right?
Yeah, it's a training size. Yeah.
So if training size is 0, then you have no training data. Is that correct? Or
yes. Yeah, it's no training data.
So training size 0, I think, is assuming already.
Yeah, the trap point. This one is actually mixture 7B gets SFT'd for one epoch on our own GPU. We reproduce the result for the Hugging Face for Hugging Face trap point. And they get slightly different because this one we use the trap point for the Hugging Face, and this one we used the GPU for our own GPU. And why? And if you want to see the same trap point, you can see from this one. And we didn't use this one because the result gets too bad. I mean, if you continue SFT, the result gets very, very bad. It only gets the 57, right?
But wouldn't that have been a fair comparison for this chart? Or you could have taken the 59.041 and then you spin on that, right?
Yeah.
I think that's why it's causing confusion, because you.
Yeah.
So both models have already been trained for one epoch,
right?
In that ultra chat data.
Right. The reason that we actually our method can directly train on the mixture 7B, but we train over the SFT model for 2 reasons. First, we want to show that the SFT model can still get improved using our spin method. And secondly, after the SFT, the model's generation will actually have the shorter length, and this would be greater for the synthetic data generation. Yeah, I'm wondering whether I answered.
So you're saying that both of the models are already trained for one epoch on this data?
Right.
And the horizontal axis is the additional training size. So you're taking it from the same data set?
Yeah, actually, the blue one, it also, the second point, it also a SFT model, but this model is actually trained it reproduced version on our GPU.
Yeah.
And if we use the model checkpoint from the Hugging 6, the result would be in this table. The result is the 57.23 after the first epoch.
Okay, another question actually.
Okay.
So, like about 10 slides ago, you had the theorem about the theorem about global optimum, where you had like the expression in one in the power 1 over lambda.
Oh.
So I wonder how did it happen? Like, isn't so say dt of yx is something like 10 to the minus 4 is like some small number. But wouldn't it be optimal to have a high value like close to 1 of dt be theta t plus 1 of yx? Like you have a theorem about global optimum, right?
Mm-hmm. Right.
In a few slides.
Yeah. You mean which theorem? Which
yes.
one?
Yes.
Yeah. This one. Okay. On the previous slide.
Yeah, this slide. So, how did it happen? Like, so I have actually trouble understanding this slide because imagine that lambda is some big number, say 1,000. In this case, this theorem is saying that we don't increase the probability of y given x too much because lambda is
right.
But how does it actually follow from the optimization objective? Because in the optimization objective, it looks like you increase the value of optimization objective if you increase p15.
Oh, you are saying that how the lambda changes the...
No, I'm confused why this is true. So if you go back to the definition of L-spin, or like where you substitute, where you substituted,
you mean this one?
The f t plus 1. Like in a few slides later, you substituted f t plus 1. Great.
Substitute the f t plus 1. Yeah, this one into. Which size?
You substituted ft plus 1 into your loss function, so you get end-to-end chaining objective. Yes,
this one.
So you are saying that the expression you had for the global minimum minimizes this expression, right? But if I look at it, then if I plug in instead of p theta yx, essentially, that decreases the right? But you're saying this is not the case. I'm confused. Because
you're saying that you plug in which p theta equal to which one will decrease the...
I plug 1 here.
Oh.
That should decrease this expression, no?
Right, because if theta equal to CRT, this equal to...
No. I plug 1 in the numerator.
Plug 1?
So p theta of ix is like if I'm optimizing with respect to theta. Yeah. So I pick p theta of ix equal 1. Why doesn't it minimize that objective? So the goal is to minimize this expression, right? This is the statement of your theorem about global optimum.
Right. Why p theta equal to 1, it will actually get smaller value? I didn't get it because p theta equal to 1, it becomes lambda log 1 divided by p theta t minus lambda times log 1 divided by p theta t. I didn't see why it should be smaller.
No, so I need to maximize this expression.
Right.
And actually, my statement is that maximizing this expression is independent of lambda because lambda factors out, right? So if in order to maximize,
it's not because here lambda is in the log function L, and L is not homogeneous, so you cannot.
Yeah, that's fine. But if I look at this expression, the theta y given x.
Okay, and you can see that p theta is p theta t times some factor that to the power of 1 over lambda. And if you take log, then 1 over lambda will goes out, and it will cancel out with the lambda. That's the reason I have the 1 over lambda over the hat. Does that answer your question?
Actually, no.
Okay, maybe we can discuss later afterwards. Yeah. And also for this figure, I want to say one more thing, that the reason that we want to train for ourselves, because that we know that training the FTT, we have the learning rate schedule, right? So you train for one epoch is not different. It's different from that you train one epoch and then train for 4 epoch is different from you directly train 4 epochs. That's the reason we include this figure after we show this result, because we want to show that even if we tune the hyperparameter of the learning rate, it cannot get the same comparable result for our spin method. Yeah.
Okay, cool. Thank you, everyone. Let's give Zixiang another round of applause for a great talk. We went over time, so we'll take any other questions offline. And thank you once again, Zixiang, for
thank you for the invitation.
Next week is actually spring break at USC, so we don't actually have an internal seminar, but instead we have 2 talks in the following week. So stay tuned for that. All right, thank you, everyone.